All right, great. Welcome back, everyone. I hope you had a nice 7-minute break from our last session. We are about to get started on the afternoon session 4A, Geology and Age Dating. And our first talk is by Bill Bottke at the Center for Lunar Origin and Evolution, one of the NLSI teams at the Southwest Research Institute. And Bill will be talking to us on the formation age of the South Pole Aitken Basin. Bill, whenever you're ready.
Okay, thank you, Brad. Well, we also take extra steps to make sure that all our speakers here are going to be on time. So let's see if I can do this. Okay. So we have a little extra preparation here. So I have this aimed at my head, and if I go long, you'll know what's going to happen. So we'll see. Okay. All right. So today I wanted to be a little bit deliberately provocative in this talk. And I want to discuss something that I think most people consider settled. And that is, we don't know the age of South Pole Aitken Basin, but is South Pole Aitken Basin the oldest basin we have in the moon? I'm going to probably raise more questions than answers. I don't know. My punchline is I don't know what the true answer is, but there's some interesting things going on. And I want the broader community to be thinking about some things. Okay, so let's jump right in. Okay, so right now, through dynamics, through modeling of various constraints and other things, we think we've arrived at a certain idea about how solar system evolution took place and how early bombardment took place on the moon. And we think essentially there's two main phases. There's a very early phase, which we're going to call from the leftovers of accretion. These are basically the leftover building blocks that were trying to make Earth and Venus and everything else, but just didn't get accreted, and ultimately they end up hitting the moon at the time. We think these leftovers are hitting the moon from almost the moment it formed till that population finally runs out. So you consider it maybe from starting at maybe 4.45 billion years ago, when the oldest lunar crust is, to some younger time. And then we think there may be a second phase where late giant planet migration took place. We often refer to this as the Nice model. And in this late migration would have destabilized many comet reservoirs, maybe many asteroid reservoirs, would have sent small bodies across the solar system. And various lines of evidence suggest that maybe this event took place at somewhere in the realm of 4.1 to 4.2 billion years ago. So that's the broad framework which we're dealing with here. Okay, and let's go to the next slide. Okay, so if this is right, using all the constraints we have in our numerical models and everything else, we've come up with a chronology for the moon. This was published in EPSL and it's Morbidelli et al. And what we suggest here are there are two phases. Let me see if I can use the pointer here. Okay, so we have a phase for the leftovers of accretion, where the population starts large and decays over time. And then we have sort of an uptick, or what we're calling a sawtooth, which is here, which is now what we refer to as sort of the classical late heaven bombardment. But that lasts for a lot longer time, many hundreds of millions of years, making basins on the moon. And this is a differential plot. And we're plotting versus the number of 20-kilometer craters we have in the moon per square kilometer. Over here is the same plot, but in cumulative. Okay, so now we're just doing everything in cumulative craters larger than 20 kilometers. And so using this plot, we've been able to come up with a chronology of sorts for different terrains on the moon. So we can see now, try to test it against things and see what kind of answers it yields. Okay, so to do this more, we have to also talk about lunar basins. So the indications are from Grail data, from lots of other work that's been done in the past, is that there's probably in the order of about 40 lunar basins, where a basin is a crater larger than about 300 kilometers or so. And the age of formation for these basins goes from a young end, maybe around 3.7, 3.8 billion years ago, to the old end, maybe as old as the moon itself, but maybe on the order of about 4.5 billion years ago. Okay. Now, what's been suggested, and people often say this, I often say this myself, is that the oldest basin we have in the moon, according to superposition arguments, is South Pole Aitken Basin. So that's this basin that we have right here. Let's see if this works. Okay. But ultimately, we have no age constraints on South Pole Aitken Basin. We just know it's old. Okay, so from a pure age perspective, it's older than all the other old basins we have. So it's older than 3.9, but we don't really know what its maximum age is. Okay, so the question is, what is that? Okay, so this is where I thought the story stood until about a year or two ago. And then I started to see interesting publications and interesting talks in the literature. And I have some of the citations down here. Vera Fernandez, Lars Borg, Grange, and others have been doing all sorts of interesting things. And they're all hinting, or they're at least making careful statements that suggest something very big happened to the moon about 4.35 billion years ago. So this spike right here. Okay. Now Borg et al. In a recent AGU talk suggests that this could even be the formation age of the moon, Or he suggested that possibly this was from a very large impact event on the moon, and he suggested maybe South Pole Aitken Basin was the reason for this. If this is right, then what you'd also have from the data we suggest is we have a pulse of magnetic activity taking place about 4.35 again. So if this is South Pole Aitken Basin, it's triggering a lot of volcanism around the moon as well. Well, I was very intrigued by these ideas, and I decided to say, okay, well, let's follow up on that and see what this kind of age would predict in some of our models. Okay. So the first thing we can do is look at the crater counts we have on South Pole Aitken Basin and on some older lunar terrains. So there's a lot of information here, but all you really need to know is this. Let me get the pointer here. Okay, so here's South Pole Aitken Basin, and here's this older terrain we have on the moon, which we're broadly referred to it as the pre-Nectarian terrain. This is one of the oldest terrains we have on the moon. Simone Marchi has done crater counts, and so here's what he gets for all the craters he counts on the pre-Nectarian terrain that are larger than 20 kilometers. Here's South Pole Aitken Basin. Okay? And so if you take these and you put them onto this chronology we've developed, you get the answers you get are kind of interesting. Okay, so the first thing we find is that according to this, in the oldest terrain we have on the moon, pre-Nectarian, has an age which goes maybe between about 4.38 and maybe 4.48 billion years ago. Okay, but then if we go to see what South Pole Aitken has, its crater population actually is less dense than this PNT terrain, and so it's actually younger. So according to our model, it would have an age of somewhere between 4.33 and 4.39 billion years ago. Okay, so if this is right, it would suggest that the age of South Pole Aitken Basin is 4.35, and that matches some of these data. So this is great, right? We match the data, we're done. Well, maybe not. Okay, but it's interesting. Okay, so let's assume for the moment that that age is actually correct, that 4.35 is right. So there's a couple of predictions here we have to consider and wonder whether this is right. So one of the first is if you create South Pole Aitken Basin, you're going to launch ejecta all across the moon. And then ejecta has to affect, presumably, other terrains that have been cratered. And so what we notice here is that this very old terrain we call the PNT terrain is pretty close to SPA. And so you might expect it to be buried in South Pole Aitken Basin ejecta. Okay? But if we look at the crater counts from this, so this is crater diameter in kilometers. This is cumulative number of craters per square kilometer. And it's a little hard to see, but if you look at the red dots versus the green dots, where the green is South Pole Aitken Basin, you'll see there's just simply no indication that the pre-Nectarian terrain had any 20-kilometer craters buried by South Pole Aitken Basin. So if South Pole Aitken Basin is truly younger, we have to explain why its ejecta wasn't sufficient enough to bury a lot of these 20-kilometer craters. And there may be ways to do that. It gets into interesting issues of how impacts deal with porosity and everything else. But still, it's a prediction. It's something we have to concern ourselves with. Okay. The second prediction that one would make is this. Okay, is that let's again assume that South Pole Aitken Basin really is 4.35 billion years ago, and the oldest lunar crust is about 4.45 billion years ago. And that's suggested by zircon data, suggested by some interesting lunar samples we have. So if that's true, then what it would mean is that we have additional basins that had to form on the moon before South Pole Aitken Basin. So if this is right, South Pole Aitken Basin is not the oldest basin on the moon, and there have to be some older things. And so you think about that, and you look at what's been written in the literature, and you go, geez, there's something wrong here, because everyone said South Pole Aitken Basin is the oldest. Well, if you look at the data, it's actually pretty murky. Okay, so one of the classic works on this, sort of the Bible of all sort of ancient bombardment studies, is this work done by Don Wilhelms in 1987, and he did a lot of age chronology and all these things. And what he finds is that there are many old pre-Nectarian basins that are so beat up, they're really hard to date by crater counts. Essentially, they're virtually impossible to date. Now, he says South Pole Aitken Basin is a little bit older than those, but really they're all about the same age bracket. And the superposition for these different basins are really murky. It's really hard to say very much. We also do not have a modern geologic map of the lunar far side. When LRO data gets finally taken in and we've done this, I think we'll be able to say more. But at the moment, again, we have it's difficult to make different relationships. And finally, this is probably the big one that's been bugging me for a long time. If you look at basins formed on things like the Galilean satellites and other things, you find basins that don't really dig a hole. And the idea is that viscous relaxation or other things is actually causing them to be fairly flat. And we think if impacts form in a crust which has a high heat flow, you might also get a fairly flat, very little hole basin. But South Pole Aitken Basin appears to be very deep. And so it always gives a suggestion that it hit into a crust that was cool, and that was possibly not younger, or let's say had been around for a longer time than maybe one of the earliest things on the moon. I've always wondered about this. So the question is, can you have a deep hole in the moon and have the crust be very, very old and filled with a high heat flow? I don't know. Okay. So what are the other possibilities here? Well, first of all, is that simply the age of 4.35 may not be South Pole Aitken Basin. Maybe we're tracing a red herring. I don't know if that's right, but we have to think about it. Okay. The other possibility is it could be maybe a simple answer. The terrain in South Pole Aitken Basin may have had a gigantic impact melt pool, and maybe it kept that impact melt pool for many tens of millions of years, maybe more than that. Okay. If that's true, then South Pole Aitken Basin could be very old, but the craters imposed upon it might be actually suggest an age which is much younger, and maybe that solves the problem. But that's something we have to think about. How long can you keep an impact melt pool going that would prevent crater formation from being preserved for some time? And then the final one is simply that our chronology, older than about 4.1, is just wrong. Okay? And that could easily be true. This is all based on what goes on with the earliest times of terrestrial planet formation. There are a lot of issues with terrestrial planet formation and what's going on with the asteroid belt, and there's a lot of work that needs to be done on all of this. And so I can think of all sorts of reasons of why this could be incorrect, and we have to think about all of them. So that's another provocative possibility. Okay. So with that, I'll just conclude by saying we have this model where we think we've been able to say some interesting things about the bombardment history in terms of an early phase from the leftovers of accretion and a late phase from what we're calling the late heaven bombardment, which is caused by late giant planet migration. If this chronology we developed is correct, it makes a prediction that South Pole Aitken Basin could actually be 4.35 billion years old. But if that's true, it makes predictions we have to deal with. There would be older basins on the moon than South Pole Aitken Basin. And also, we have to explain why South Pole Aitken Basin didn't bury the moon in a whole bunch of ejecta that would erase 20-kilometer craters. So the question is that kind of prediction geologically possible? And that's it. I'll stop there. Thank you.
Great provocative talk, Bill. There are several comments in the presenter questions you can read for yourself. Barb Cohen made a comment that you can read, but she asks also, what determines the slope of the old end of the flux curve in the sawtooth model? By making it slightly steeper, there would be a smaller interval between the crater fluxes observed. Can you comment on that?
Yeah, well, the decay curve. So if you go to the oldest, part of our chronology, if you're dealing with the decay curve, we're actually getting that from some runs that Alessandro Morbidelli has done, taking some of Kevin Walsh's results on what they call the grand tack and wondering how the planetesimals go down. Now, that curve could have a lot of different shapes, but we also have to fit the total amount of highly siderophile elements that are delivered to the moon that have been estimated from what's being in the lunar mantle and everything else. So that sets to some degree how much of a flux we can have. So if those numbers are off, we also have to say something about how we can have them be off and still accommodate the amount of highly siderophile elements we have in the crust and in the mantle. So it's set by dynamics. The dynamics could be wrong, but we still have constraints we have to deal with.
Great. And Brad Jolliffe writes in, and I believe we can all agree with him. He says, Bill, very provocative. Seems to me we need to go and get samples so we can make a direct determination. I think everyone's in total agreement with that.
Let me just say this, and that's absolutely true, and but for another reason, right? So it doesn't really matter if South Pole Aitken is the end of the line or sort of the middle of the line. It's telling us about the final stage of planet formation. Okay, it's telling us about the leftovers of accretion. If we want to understand the formation of planets, you have to understand that phase. And the lunar terrain, especially some of this pre-Nectarian terrain, is some of the oldest stuff we have in the solar system. I mean, new work is suggesting Mercury's terrain doesn't come close to being as old as this terrain. Okay, so if we want to understand the very earliest times of solar system history, we have to go and sample the pre-Nectarian terrain, and the South Pole Aitken Basin is a fantastic place to go and do that.
Great. I also had a quick question. I was wondering about your comment about the fact that South Pole Aitken Basin dug a big hole and how it's possible that there was a cooler crust at that time. Can you make any comments about how that ties into the current models of the lunar magma ocean and the thermal history back during that time?
We're going very far outside my comfort zone because I don't do this. But what I found very interesting is that there certainly are hints, when you look at the moon, for some craters that appear to be very old, that we can find no evidence that they actually are basins, and yet they still appear that they might be basins. Things like Mare Tranquillitatis. Tranquillitatis is possibly a basin, but maybe it formed when the moon had a very high heat flow. So these are interesting questions. I mean, the issue is you can imagine the front side of the moon having maybe a different heat flux overall than the far side of the moon. Maybe the far side of the moon has always been except right after formation, maybe it cooled down much more quickly. And so you're dealing with different animals when you deal with the near side and the far side. Some of this gets down to precisely what Grail has been talking about and some of the things they've been doing. And it's all very interesting, and I'm sort of at the beginning of my understanding of all this. So there's a lot to do.
That definitely ties in with Vera Fernandez's comment about the ways that the crust potentially didn't cool simultaneously and homogeneously.
Absolutely. I mean, another provocative comment. You could imagine that the near side of the moon, let's say the big area, which we often call the prosolarian creep terrain, let's say that was formed by a giant impact, a giant prosolarian impact. If that's true, you would have a natural way to explain the differences between the near side and the far side. And the near side maybe doesn't have a crater there because essentially it excavated a lot of material, but also the heat flow was so high it actually caused it to sort of smooth down and be flat. And so you would have a natural reason why South Pole Aitken Basin and Prosolarium could be very different and yet be on the same moon.
Yep. Great. And there, I think some other folks were typing, and I think we'll take them offline into the general chat from now. But thanks much for the provocative talk, Bill. Appreciate it.
Thank you. Oh, and I'm actually changing my chair now. So Moni Markey's going to take over.
Great.